Hello again. So, so you want to write a Vulkan renderer in 2025? Of course, I have to start with who am I? I'm Charles Giessen. I've been using Vulkan for many years now. 2017 was when I was a student, really getting into it. In 2019, I joined LunarG. I've been helping maintain loader, API dump, a bit of validation layers, lots of SDK work, um, all sorts of small things. In my free time, the Vulkan community is commonly finding me on the Discord server, helping moderate and just answer questions. And I like talking with people, and I have talked with many people about writing Vulkan code based on my own experience, listening to them, comparing, contrasting. And so the reason I'm giving this talk is because I want to explain what I think is a way to write a Vulkan renderer in this year, which of course I have to disclaimer that it's less of a technical talk and more of a not philosophical, but primarily here are high level patterns to follow, high level conceptual talk. That's the word I was looking for. They are all strictly my opinions. I don't write renders day in, day out for LunarG, so I can't give you my, big game engine X opinion because I don't write big game engines. It's primarily with desktop Vulkan. It's what I work with primarily in LunarG, and just that's my own personal experience. Notice that desktop is not Android. Android has fundamentally different targets and use cases, and I cannot speak to those directly. I tried to make this talk as broadly applicable as possible, but your experience may differ, and that is perfectly okay. Vulkan is huge. 5,000 page PDF document, 5,000 plus page. There's no way in the 30 minutes I have I can cover everything that we could cover. And it's not possible to drill down into rendering algorithm specifics because every use case is different, where different rendering algorithms will, whether you use ray tracing or not, that's a huge question. And I cannot answer that for you. And I'm not even going to attempt to try to do that because that'd just be dishonest. So I'm going to be focusing on the Vulkan parts of what rendering entails. So let's just get started. How do you design a Vulkan renderer? Step one, you just pick the API version you're going to use. Step two, just pick the extensions you're going to use. Step three, and then profit is step four as the final step. So let's get right in. So what version should you target? Well, whatever your hardware minimum is. If you can set your hardware minimum, then you know your answer. That's a bit of a cop-out. What is your hardware minimum? I don't know. I can't tell you, but it depends. For desktop, it's relatively easy for me to say you can use 1.3. In the Blender talk, we heard that, oh, wow, there was a lot of things that we could just use 1.3 and that'd be fine. Same with your talk with using Rust. Unfortunately, Android is not so easy to just say, I use 1.3 and you're fine. It's not like you can't use 1.3, but if you're having to define your hardware minimum, you might find yourself going, okay, we'll start with 1.1 and add things as we can, but we'll always support 1.1. Similarly, with desktop, you could always say, well, I'd like to use 1.3, but I'll go 1.2 or 1.1 just so I have maximal support. And that's fine. It's a hardware minimum, not a maximum. Mac OS, it's very close to being fully 1.3, but as of yet, I would say it's 1.2 with almost the feature set of 1.3. I don't remember the exact details, and it's changing as people create more PRs and they get merged in. Two extensions to go. That's so close that you can almost say you can write a 1.3 application and then just sub out it into the 1.2 respective component. Yeah, I shouldn't speak for multi-VK. That's not what I work on. 1.4 came out in December. That was 2-3 months ago. Saying you should just use 1.4 is a bit disingenuous because people have to update drivers to get the new driver version that says they're 1.4. Even if the hardware will support it, eventually, not all your users are on driver versions that will have it already. And telling users to go update your drivers is okay in some contexts and not okay in others. Little side tangent, there are actually 3 versions. Oh, I had 4 up by accident. 3 different version numbers in Vulkan. The instance version, you get it from the loader, the libvulkan.so, vulkan-1.dll. That's the thing that all your applications link to and subsequently get the drivers from. The function enumerate instance version will tell you what instance version you have. If this function doesn't exist, you are on a 1.0 driver. So that's your version. A more important version than the instance version by and large is the physical device version. You get it from the GPU driver, specifically if VK enumerate physical device properties, and on the struct that you get out of it, the API version. This is what tells you what the hardware really is capable of. You could have a 1.3 instance and a 1.1 physical device, and 1.1 is what the hardware supports. But that is what the hardware supports. You, as an application, need to say what you are going to use through the application API version. And I forgot to make that code snippet be dependent on the slide animation. So it's been there the entire time. But yes, you just, when in your VK application info, you'd set your .api version. Note that this is an instance level version, or this is an instance level construct. So you pretty much say, oh, I know how to use 1.3. And then if your hardware is actually 1.2, then in your application code, you have to do the steps to use 1.2 if you have a 1.2 driver, but a 1.3 instance. Now, all of that said, typically the driver and instance version are lockstep because the driver will install the loader and that will be the same version, or it's managed by the system and the package manager, and those will stay consistent. But sometimes they're not, so that's why I give it out. Okay, that was step 1. What's step 2? What extensions to use? Quick explanation. There are 2 types of extensions, device extensions. Almost all extensions are device extensions. You get them from enumerating the device extensions. How prophetic. Many of these have been promoted into core versions. So there's a lot of extensions, and then some of those are actually just what are in core, but are also available as an extension. Instance extensions, not many of them. You get them from enumerate instance extensions. Woo! There's the VK device, VKEXT debug utils is easily the most like, yes, you should use this. Please use this. You'll make your life so much easier. Has so many good things. And the other instance extensions worth knowing about are the platform WSI extensions, because that's how you get stuff onto the screen. There are other instance extensions. They're useful, but they're not that commonly used. And whether you need to use, the less said about them, the better. Because there are over 300 published extensions, device extensions, mind you. And while every extension solves a problem and they fix one small call site, some of these extensions are huge. They cover half the API, it feels like, with new capabilities and new VUIDs to worry about. So which ones you should use, it heavily depends on your use case and what you need to use. As before mentioned, the hardware minimum and the target version are all both major constraints. What platforms you're going to be working on, because Windows versus Linux, they might be running the literal same hardware, but their drivers might not support the same things, and that's a consideration to make. And just the more variability in your code paths, the more maintenance it is to implement, test, and validate the code you're writing works as you expect. I just have no time to cover each extension individually, and the whole genesis of this talk is Vulkan is massive. What can I cover in 20 minutes that should save you time down the line so you don't have to go and research all this stuff on your own? You can be given the search SEO terms that you can then go and look into more detailed on your own. Still, I'm not really telling you which ones to choose. Some of them are aliases to core function. I did mention that. But some are just aliases to other extensions as we move things around, update them. Some have dependencies to other extensions. So if you wanted to use this extension, actually, you'd also need to use this one. That's an annoyance. Whenever you use an extension, there are feature booleans you often have to enable. You're querying these through the physical device features to pnex chain and then enabling them in the VK create device pnex chain. Core features have very helpful core feature structs. Physical device, Vulkan 1.1, 1.2, 1.3 features, and extension features have a struct per extension. The actual mechanics of checking for features, checking for how to enable them, and various mechanics of that. The Vulkan guide has a lovely write-up on that just details it and keeps me from being just a boring, if this, do that, if this, do that type presentation. I would be remiss if I didn't mention Vulkan profiles, because they are the working group's response to, wow, we have a big extension soup. What can we do to help address that? And the Vulkan profiles defines explicit extension and feature requirements so that a user could choose a profile and that is their baseline target, rather than having to manually choose each extension based on what their needs are. People can collectively put that knowledge into one place. As it turns out, my example for a profile was a poor choice of example, because a VP Roadmap 2024 is not a profile you should be using. It is a profile the working group defines for their purposes. It is, however, the first profile I found in the specification when I was putting this slide together, because I wanted an explicit, okay, if someone asks, what is a profile? And I can tell them the technical answer, but they no. I want an example of one that I can look up myself and see what is exactly in this JSON file. Well, here it is. It's in the spec, so it's always available to access. But that's not the profile you should be using. Various engines and tools and frameworks put out their own profiles. LunarGS have various baseline profiles, portability profile. Android has its own profiles, and those will tell you what your baseline targets are of things first. And they do it. There are different profiles for different years. So if you're saying, I only want to have to support hardware that's 5 years and newer, 5 years old and newer, then you can choose that year's profile. There's also the profiles tool set, which is a library that automates enabling the features for you. And that's just a very handy thing. Yeah, I've described that. But Vulkan is big. Vulkan 1.0 is smaller. Why not just say, okay, all this features and extensions and version nonsense, why can't we just go right back to 1.0 and just use that? It's single target. There's no guesswork. You can find the original 1.0 spec, which would be 8 years old now. That actually would be a fun history trip. But it'd be supported everywhere that Vulkan is supported. I've said Vulkan is massive, but even Vulkan 1.0 is hard enough to learn that you're being told you should learn Vulkan and all the new stuff. That's overwhelming. That's a lot of things. And learning Vulkan requires either forgetting or reinterpreting your past knowledge from other APIs. OpenGL, in this case, is a lot of the OpenGL concepts do not map to Vulkan, and you have to just relearn how you do graphics. All sorts of new concepts, render passes, and synchronization, and descriptor sets, and I can keep going and going. There's more than the slide fits. New things, new problems. The Vulkan 1.0 is a spec that is 1.0, not the best version that ever existed. How many of you have written something and the first time you compiled it, there were no compiler errors and it ran perfectly and it met all your feature requirements and no user bugs were reported? No, that never happens. The first version is the first version and it gets better over time, but it was the first version. I mean, there was lots of clunky-ish interfaces. There's lots of interactions that I'm sure the working group thought about, but when you put it into the hands of the users, then you find out all the actual interactions that matter are not as obvious when you're just writing the spec. And there are some missing things, but that's not as big of a deal because you can add them back in, which is what has happened. Yeah, picking extensions and versions and features, capabilities, and limit, all of those things is hard. But I would argue that 1.0 is just harder. And that is what the rest of this talk is really going to be about. It's that we aren't stuck on 1.0. We're in 2025. Has anyone realized that? I mean, the New Year's was a month ago, but like it sometimes takes 2 or 3 months for me to remember what year it is. So the working group has been very hardworking and fixed basically all the big problems that 1.0 had. Um, it's it's disingenuous to recommend 1.0 when we have all of these things that make it so much easier. So, what is a good example of a 1.0 type problem? Well, it'd be immutable pipelines, monolithic pipelines, where you take your compiled binary of inputs and you bake it once, but you have to costly do that ahead of time, which okay, well, you only have to do it once, right? That's you can amortize that. Well, even if you only need to bind that, even though you can bind it many times, and that's a cheap operation, you're exchanging time and space because your startup time gets put into conflict with your runtime. I put a picture up of the pipeline state. This is actually a simple diagram because the current spec has the mesh shaders and ray tracing in here, and those add all sorts of new elements to the pipeline. Yeah, anyone who's used Vulkan will intimately know that you need to create a new pipeline for everything because you have to know about it ahead of time when you create the pipeline. Inputs to the pipeline, if you have a different shader, you're going to need a different pipeline. If you're going to have a different blend state, you're going to need a different pipeline. Here is just some smattering of different things that influence a pipeline, and every one of those is a different input vector or into the combinatorial explosion of various variants. I've I can definitely say 10,000 pipelines is a number that many titles ship with. And in some game engines, they push that number up an order of magnitude, which is a bit scary, but they make it work, I guess. Uh, but I've seen many a loading pipelines, please wait. Loading pipelines, please wait. It takes time to create all those pipelines, even if you're doing it ahead of time. That isn't necessarily a solution. I mean, maybe you have less stutters, but sometimes you don't know what pipelines you are going to need, and so you have to do it just in time, meaning you do need to figure out some way to prevent the stutters from being too bad. That was a lot of explanation for VK dynamic state as the, I won't say only solution, but it is a primary solution for reducing that combinatorial explosion of pipeline state. Because even in Vulkan 1.0, the API designers realized that not everything had to be fixed. Lots of things were already dynamic in hardware and were exposed as that. Dynamic viewport and dynamic scissor being my two favorite dynamic states just because they've always been there and they make everything nicer. When you're using dynamic state, you set the dynamic state during command buffer recording time. There's 70 different states now that can be dynamic. If you want a great reference, Vulkan Guide has it for you. If I tried to list that out on the slide, you wouldn't be able to read them because that's too many to fit on a single slide. And they come from different versions. Some are from Core 1.0, some are from extended dynamic state 2, and promoted into Core at various times. And so which dynamic states you can use and which dynamic states you should use depends on what your baseline is. So I recommend referencing more complete tables than I can give you. But reducing the combinatorial explosion isn't the only aspect of pipelines that are kind of kludgy. Just having pipelines at all means you need to compile them. And that is in some cases a problem. This slide is less, you should use this, and more informational about what is coming and what currently exists. The graphics pipeline libraries extension breaks pipelines up into bits that can be quickly linked together at runtime. It helps with the variant costs where you can create your parts of it, and then as you figure out exactly what you need, you can combine them together quickly. And the shader object extension goes at it from a different angle and drops pipelines and just has compiled shader stages. And there's limited support for that. So shader object is even harder to recommend, but both of these are not work in progress extensions, but they are indicating what the future may hold. So there's not a single way to do things. Where we being the Vulkan world is still figuring out how best to solve the pipeline problem. The other big 1.0 snafu, render passes and subpasses by definition. I stole this slide from Sasha Willems. It's a lovely example of a simple gbuffer rendering of a render. Anyways, what is a render pass? Well, it's whenever you do rendering. In Vulkan, we have a definition of what that means. And in 1.0, we define that as this object, a VK render pass. And we define that all drawing commands, not compute dispatches, but VK command draws and similar, must be inside of a render pass. It acts as a pseudo render graph. You define your inputs, you define your outputs, you define your subpasses, and it exists to allow the driver to efficiently schedule your rendering work. And explicitly it is there to help tiling GPUs better use the memory bandwidth that they have to do rendering efficiently. When you're creating a render pass, you got to describe your input attachments, meaning the images you're going to be reading from, writing to, being as transient, and other similar things. The subpasses, the explicit steps in your render graph, or render algorithms, and then the dependencies between those steps so the driver can figure out the best way to organize it. And render passes are great in theory. They were not that great to use in practice. The single object with multiple responsibilities, that's a common theme in programming practice paradigms. It's like you should have one responsibility for one object. And while I don't believe that's true in all cases, in this case, a render pass object absolutely tied in many different things into a single object, which made that a bundle of state that just made the API harder to really reason about when you're looking at the code and how the API interacts. I mean, it defined the attachments and memory barriers and the subpasses, and through one object, all of these things get funneled together and, you know, bound up, which created for a really hard architecture because everything had to be defined in terms of these render passes to be made useful. Talking about pipelines for a brief second, render passes were another dimension of your pipeline state, pipeline combinatorial matrix. Every different render pass meant a different pipeline. And for many on the desktop side of things, the tiling GPU focus of it, it meant that the benefit of a render pass for non-tiling GPUs was minimal, if any, and that whenever there's API friction that you have to do, even though it doesn't do anything for you, that feels very unfun. And, you know, this is my bias again showing. If it's commonly found in mobile and I'm not doing mobile, I'll latch onto it as the thing that I'm like, rah, 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 rah. But my bias, not you, so that reflects poorly on me, not you. So render passes require frame buffers. I just want to point out how fun it is to name things, and frame buffers are confusing because everyone who comes, oh, it's a frame buffer. And it's like, well, really, it's just a couple of image views. You're like, but what do you mean? And it's like, well, yeah. And that's just falls out of render passes defining everything in your architecture. So dynamic rendering is introduced and the world rejoiced. No longer in 1.3 as default and required, or there's the extension for before then. You can just drop render pass objects entirely and say inline, start rendering with these attachments, and then you do your rendering, and then you go end rendering, and that's it. Application architecture becomes a question of how you're going to do your command buffer recording, not how you're going to sync up your pipeline creation and render passes, because now pipelines just need to know what the image layouts are of the attachments, not all of your rendering architecture and subpasses and memory barriers. And while dynamic rendering makes things simpler, it doesn't mean you don't have to do synchronization. You had to do that with pipeline, with render passes, but that was bound up in the render pass creation. Now, the synchronization between various things is you have begin rendering, submit barrier, or command barrier, and then command draw, and then command barrier again, so that it's very explicit what you're doing in your rendering. And I think dynamic rendering makes the Vulkan's explicitness actually more true to its claimed nature. Tiling GPUs aren't left behind. I know I like to think, oh, they're just going to be playing catch up, but no, dynamic rendering local read is the extension and feature that brings tiling GPUs up to the same capability and not needing to state the render passes. And frankly, I have a very hard time suggesting that you should use render passes if your hardware isn't new enough, because it's not really fun. Is there an emulation library for render passes for dynamic rendering using render passes on old hardware? I'd love for that to be a thing, because then you can just say, here's my library, it does it for you. But maybe that's something I should write. Who knows what the future holds? Okay, that's enough about render passes. Let's move on to the way to get data into your shaders, and that's through descriptor sets. Oh, it's my time. When did I start? 11:45? Yeah. Oh, wow, I am going to have to speed up. Okay, descriptor sets. They do things that provide data to the shader. They're not very great in the base thing. Not that they're bad. They do their job very well. But in one sentence summary, they're very much forcing a specific rendering style where you have triply or quadruply nested for loops where you bind your things based on usage and then rebind descriptor sets as needed. Many of us are moving towards bindless rendering where you just bind everything once and in a one big descriptor set and then index into it at will, of which Vulkan 1.0 does not greatly support. The other aspect of 1.0's limitations are the descriptor count being quite low. So descriptor indexing comes in and lifts the limits. It allows non-uniform indexing. It means you can update your descriptors more freely, and a whole lot of other small things that just make life easier for certain use cases that are very, very powerful. Because I'm running out of time, buffer device address is awesome, and if you can use it, great. It allows you to just use pointers instead of VK buffers and BK buffer views. That's great for certain algorithms, pointerific data structures, trees, and stuff. Talking about things in the future, descriptor buffers are another way to do things. Whether they're the way to do things now is a judgment call you're going to have to make. It does mirror the D3D12's model, so if you're trying to go to Rust from it doesn't. Oh, today I learned. Maybe I'm messing up with something else. Oh, whatever. Okay. Shader memory layout. Here's a fun question. I'll let you mull over. How do you write a C buffer that mirrors the data layout of this GLSL struct? If you have an answer, tell me afterwards. And here's a different one with a different layout. And I'll cut to the chase. It was a trick question. I didn't tell you what the layout was. How can you know what layout on the CPU you need to use if you don't know the data layout on the GPU? 3 different layouts that are available. And scalar block layout is the layout to use if you don't want to have to think about the layout, because it mirrors the C API. And so if you know C, you know what the ABI, not API, sorry. It matches your expectation. Whether you should use it or not is, again, up to your discretion, because memory bandwidth is a very common performance problem, and the way you lay out data greatly impacts that. So I'll let you be a judge of that. If you want more information on both scalar layout and the other 2 ones that I didn't mention, again, Vulkan Guide has a great reference for this. Synchronization, many different kinds of sync. It's complicated. I think everyone who's tried Vulkan knows this implicitly, and I don't need to reiterate that. Timeline semaphores are the first step to making things easier by allowing you to have a single value that you just increment. VKQs match well with this, because VKQs are where you just push work, and that timeline semaphore can then just go, okay, I'm going to match it with a counter value. Allowing you to sync between the host and the device is just a very nice way to keep your application all working together. Being able to wait before signal is a really nice feature that you can't do without timeless semaphores. Only downside is the lack of swap chain support, so you'll have to have a couple of semaphores to work around that for the current time. Synchronization 2 reorganizes the API of Vulkan to be just nicer to use with synchronization, making things that were not connected, so it's easier to understand what's happening and understand how to use the API most efficiently. I think and Vulkan Guide also has a good article on what it has. I'm going to skip through this quickly. Shader draw parameters. They were missing. They've been added. It's great. Indirect rendering. You could do indirect rendering, but you couldn't get the count from the GPU. You had to use a CPU buffer or a CPU value. That sucked. And that's been fixed with an extension and then core feature, and I think 1.2 it was added. That lets you say, okay, here's an indirect buffer, and the number of commands in it is indirect as well. Device generated commands. It's really cool. It's a bit early to say go and use it, but it may solve problems that you don't know you have, and it is where things may be going, and I think that's really cool. And it's also my last slide, so that's why I'm trying to skip through it quickly, because my conclusion is Vulkan Guide. Actually, just use Vulkan Guide. Just look it up, look at all the articles. It tells you so much information. It's open source, and it's not a spec, so you don't have to do that. Vulkan 1.0 is the start, and the new stuff is worth the time and effort. So thank you.
I think we'll try and squeeze in 2 questions.
Mine's short. It's just a comment. Yes.
Thanks for that.